Okay, so good afternoon, ladies and gentlemen, and thanks for joining this lunchtime seminar organized by the Young Submittee Group. Before starting, it's my duty to inform you that the meeting is recorded, so please turn off your camera and your microphone to avoid background noise. Questions will be kept at the end of the seminar when you will have the chance to either unmute yourself or write them in the chat box. Today, we have the honor and pleasure to host three young and brilliant researchers from University of Bristol who will be sharing insights on the very interesting and fast developing topic of digital twins models, which are interesting forecasts to sustain half of all large industrial companies by the end of 2021. In particular, we have Maria, Sam, and Elia, who will be sharing some of their work done to develop a digital twin model of the Clifton Suspension Bridge in Bristol as a proof of concept study. Worth to mention that this project has won the prestigious Seed Corn Funding Award 2021. More about the speaker, Dr. Maria Pregnolato is a lecturer in infrastructure resilience in the Department of Civil Engineering at the University of Bristol. Her work focuses on infrastructure resilience, in particular the impact of flooding to road networks and bridges. She holds a Living with Environmental Change APSRC fellowship to investigate the impact of extreme loading on bridges and transports. Maria will provide us with an intro on the topic. Dr. Elia Voyagaki is a senior research associate in earthquake engineering at the Civil Engineering Department of University of Bristol, and she will be discussing the history of the Clifton Suspension Bridge and the finite element model of the structure that she created. Sam Gunner is research associate in the Engineering System and Design Group at the University of Bristol. He's an experienced electronics and system engineer who has developed and deployed a range of novel data gathering systems, and he will be discussing the structural health monitoring system of the structure, firstly the one that they developed and deployed in the past, and then the one that they plan to use in the bridge and as the flexible monitoring test bed in the future. Maria will then provide us with some conclusive remarks. Now, without further ado, I will leave the floors to the speakers. Thanks.
Thank you, Valentina. Thank you so much for inviting first, for the nice introduction and everything. Can you see my screen?
Yes, I can.
Perfect. So thank you so much. It's very a pleasure to give this talk, especially because it's actually the first one that we are giving on the first outputs of this case study and the future steps that we are going to encounter. So the term digital twins has become very popular nowadays, and it's really propelled us in a sort of future dimension. But actually, the concept is not new at all, and has been followed by mankind for centuries. For example, even in the ancient Greece, we can find some mechanical twins of the solar system with which people were trying to study the movement of the planets. Of course, however, we have to wait for the advancement in computing technology in order to really have the difference that led to a digital twin. And the first contemporary digital twin can be found in the mission of Apollo 13 in the 1970, when a digital virtual model of the spacecraft was built by NASA in order to understand the behavior of the object in the space. So this is really seen as the first contemporary prototype of digital twin. However, we have to wait for few decades of more silent simulation models before arriving to a sort of declaration of digital twin that is usually recognized to Dr. Michael Greaves, who started the digital twin concept in manufacturing in 2002. And after these terms was also officialized with the roadmap report of 2010 by NASA again. And from this year and after, digital twins have really flourished in the manufacturing sectors, especially in wind turbines, oil and gas, Formula One, and other production. However, it doesn't really apply to civil engineering at this time. We have to wait for 2015 when the Center for Digital Britain was created in order to push the digital development of the UK. This is a very special group that is targeting the digitalization of the built environment and of the wider architecture, engineering and construction sector, which underpin the report for the National for Public Good and also especially the Gemini Principle. The Gemini Principle is a very good report which actually underlines this principle for twinning as a roadmap for bringing to digital twins. These digital twins are seen as federated as a system of systems in order to provide the national twin for smart cities. Of course, before getting to these points, there are still much work to do because digital twins for civil engineering has actually just started, especially in practical terms, and much work there is still to do in order to bridge the gap from the theoretical level to the practical one. But what is actually a digital twin? So the digital twin component sees a real object, which is the real structure in the case of infrastructure or the real building, and then its virtual or digital counterpart. And the important part between the two is constituted by the link, which is the connection made by data and historical information and any other points that can make the connection. Traditionally, this link has been considered at real time. So the updating between the real information and the virtual counterpart were made at a near real time or just at time. However, for civil engineering, this concept has been reconsidered in order to consider it the right time. So the time of frequency of the twinning rate that is more appropriate to update the virtual model. This, of course, depends from the scope of the digital twin, because if the scope of the digital twin is to monitoring, like just for regular maintenance, this right time could be once per month. However, if we are monitoring like some extreme events, this could be an hourly updates. So this concept of twinning is very crucial in the twinning process. And the last step, which I called experience, I think is as important as well, because a digital twin is useless if it is not connected to the reality. So this experience includes all the operational context that makes a digital twin a responsive system. And this could be, for example, the identification of thresholds that allow to support or to trigger decision makings and management plans. So why building a digital twin? So first of all, trillions of dollars are spent worldwide each year on inspection and monitoring. And the traditional procedure of this inspection are not really based on smart or intelligent system, but are quite visual. And if I think about flooding procedures, for example, they involve divers. And so all these techniques are quite expensive and even not very safe in many cases. So it is predicted that by using digital twins for maintenance planning, for example, the cost savings could arrive to up to 20–30%. And maintenance is just a part of what a digital twin can do. So the investment in this case would be heavily compensated, because the digital twin can be used for design, construction monitoring, equipment tracking, visualization. So it's like having a tool for testing your options before they are deployed in the real world. And now is the right time to think about digital twins for civil engineering, because there is the maturity of the technology. So you can think about the Internet of Things, artificial intelligence, machine learning. We have so many techniques with which a digital twin can benefit from. However, the practice uptaking is a bit behind, especially compared to the technology advancement, since there is still the need to demonstrate the value of the digital twin. Since a digital twin requires a very high range of expertise, also costly equipment, and so sometimes the business case behind is a bit difficult to be identified. Also, there is the need to develop the confidence and the trust of owners and infrastructure operators in order to start using such a tool to changing their routine and their forma mentis. So this project is within a wider program that is called UCRIC, that is the UK Collaboratorium for Research on Infrastructure and Cities. And essentially UCRIC is looking to create or collect data for infrastructure renewal in the wider sense. And one of the tools of UCRIC are the urban observatories and the city dashboards in order to collect and create this data within an infrastructure that is functional for value delivery. In particular, in Bristol, we have one of these 8 urban observatories, and our focus have been on water quality, air quality, both indoor and outdoors, and transport such as electric bikes. Of course, there is also the monitoring of infrastructure, structural health monitoring, and the Clifton Suspension Bridge is the case study for this topic. Working with the Clifton Suspension Bridge has been really exciting for me, because it's amazing to use a symbol and such an iconic structure for our city as a testbed. And we were very lucky to have this precious relationship with their owners and operators, the Clifton Suspension Trust. The history of the bridge also is very much fascinating, and so I think we were very lucky to have, and we are still to have the occasion to work with such an infrastructure. But now I will leave Elia to talk more about the bridge for me.
Hello, can you see my screen?
Yes, we can.
Okay, thank you. So hello everyone, thank you for attending this seminar. My name is Elia Voyagaki. I'm a researcher
Sorry,
in earthquake engineering.
It's not shared like a screen view. Or at least I can't see it.
So you cannot see my screen?
I don't see the view mode.
Let me. Okay, let me try again. What about now?
Yes, it's good.
Okay, so hello everyone, thank you for attending this seminar. My name is Elia Voyagaki. I'm a researcher in earthquake engineering at the University of Bristol. As Maria very nicely presented in the introduction, the case study we are applying our digital twin methodology is an iconic structure, the Clifton Suspension Bridge. In the next few slides, I will focus on its history, which is quite fascinating, the uniqueness of its design, the reasons it was selected for a digital twin, And finally, the first steps towards a digital twin that involved a detailed 3D finite element model we have been developing together with my colleague, Dr. Raffaele De Risi at the University of Bristol. I'm not sure. Okay. For some reason, I cannot change slide. I'm not sure what's the problem. I cannot change slide. I'm not sure.
Would you like to share that I share the screen and you talk and I?
Yes, please, Maria. Let me stop sharing.
Okay. Can is it okay? Is my screen showing well?
Yes.
Okay.
Excellent.
I'm sorry, Elia.
I don't know what happened with my computer. Okay, Maria, if you can go to the second slide, please. Okay, excellent. Thank you. So let's start with some facts about the structure itself. The Clifton Suspension Bridge is spanning the Avon Gorge and the River Avon, linking Clifton in Bristol to Lee Woods in North Somerset, and forms part of the B3129 road. Since opening in 1964, it has been a toll bridge, the income from which provides funds for its maintenance. Maria, if you go to the second slide, please, to the next one. The history of the bridge is fascinating and involves the biggest name in Georgian and Victorian architecture. Maria, I think you need to go to one slide back, but it's okay.
Can you see my screen?
Yes, I'm in the previous slide. No, you're going forward.
Yeah, this is one.
Before that?
Yes.
And there are two slides in between.
No.
It's okay. I'll take you through them very quickly and go forward. So the history of the bridge is fascinating. It begins in 1754 with the wish of a wealthy Bristol wine merchant, William Vick, who made an investment of £1,000, indicating that when this figure reached £10,000, it should be used for the purpose of building a stone bridge that would connect Bristol to Somerset over Avon Gorge, and also because of its height would allow large ships to travel on the river. In the 1820s, Vick's legacy was close to 8,000, but it was estimated that the stone bridge would cost 10 times more. So, by means of a parliamentary decree, a steel suspension bridge was allowed to be built in place of the stone bridge, and they started to collect fees for the construction. In 1829, there was a competition to choose a project for the bridge. The judge, Thomas Telford, who was also a designer, rejected all other designs by insisting on his own design. So a second competition was held with new judges, and Brunel's design was the winner this time, with a suspension bridge with Egyptian-influenced towers. So they purchased the cables, they built the towers, and then in 1843, before adding the Egyptian-style finish, they ran out of money. They stopped and they stole the cables, who were then used in another project by Brunel, the Royal Albert Bridge in Devon. In 1859, Brunel dies. His colleagues, considering that the completion of the bridge would be an appropriate memorial, started a campaign to raise new funds to complete the work. So Brunel's design was then revised by two eminent engineers of the time, William Barlow and John Hawkshaw. The deck was replaced by a wider, taller, and more robust one. The two chains initially proposed by Brunel were replaced by a three-chain catenary system. The towers remained in rustic stone and without the Egyptian finish. Construction resumed in 1862 and was completed 2 years later in 1864. But let's look into more detail at the structural characteristics of this wonderful bridge, which is very unlike any modern bridge that would be built today. It is much more dynamic than a modern bridge, lighter and more flexible. It is made of wrought iron, wood and stone. It has a span of 214 meters and a width, including pedestrian crossings, of 9.5 meters. The height of the towers is 25 meters, and the deck is relatively light, made of timber with wrought iron lattice cross girders in line with each pair of 82 iron suspension rods hanging 100 meters above the river. The suspension chains supporting the bridge on each side of the roadway are formed as a system of 3 wrought iron sub-chains arranged as shown here in the pictures, one above the other. These sub-chains are made of long iron bars with special eye joints at their ends. Each link of each chain is formed by 10 to 12 bars arranged side by side. Suspension rods are attached every 2.5 meters to each of the 3 chains in turn. Now, a key part of the catenary system, the main span chains, no, Maria, please, yes, thank you. The main span chains and the anchor span and the anchor chains are connected at the top of the towers through a system of vertical iron plates bolted together between a pair of iron castings sitting on a cast iron plate on rollers which run on another iron plate. As I don't know if you can see clearly in this picture. The anchor chains are supported through land saddles that guide the chains through a 25-meter shaft inclined at approximately 45 degrees to reinforced anchorages. The tower rollers facilitate changes in catenary due to load or temperature changes, and also minimize the transmission of longitudinal forces from the chains to towers and land saddles. This is possible only given that the saddles are free to move. If they stop moving, this could significantly increase the strength the stress on the rock abutment, and this abutment is a natural structure, and so exact operational stress thresholds are not easy to measure. There is therefore an operational imperative to ensure that the frictional coefficient of the saddles is kept low. In terms of management, the bridge is managed by the Clifton Suspension Bridge Trust, who since 1952, by an act of parliament, have to preserve and operate it forever. This is not a simple task, as the bridge is important, is a very important route into the city from the south and carries a lot of traffic. The annual flow is 3 million vehicles, as well as pedestrians and cyclists. Moreover, it is one of Bristol's more visited tourist attractions in its own right. So how can we support the Bridge Trust in their mission to operate the bridge forever? And what information could we produce to support their decisions? There are a lot of considerations that impact the operation of the bridge. The supporting roads have been known to break in the past, and an ability to predict this would help optimize maintenance. The rock abutment on which the Clifton Tower sits is a natural structure, and so strength cannot be guaranteed. Can anything be done to minimize the load on the abutment? We just mentioned about the saddles. The bridge deck is much more flexible than in modern bridges. I'll get a bit into the detail of what this means in a second. But the result is that the bridge is more susceptible to something called flutter, which is induced by high winds. All these are operational considerations, information about which might help the bridge master keep the structure operational for as long as possible. Now, we don't have an operational digital twin yet, but we are working on it. And I'll go through some of the components that we do have to give you a flavor of what it will involve. A big part of the digital twin is the finite element model of the full structure that should be in conversation with a monitoring system and use the data towards predicting critical response patterns, as well as update its properties using real observations and data. For example, critical components requiring monitoring are the response of the iron chains, the stresses on the chain, and the movements of the tower saddle. We have collected as much information as possible with the help of the Bridge Trust and COWI, as well from John MacDonald and the previous work from the University of Bristol team. Blueprints of the bridge, details, reports, published papers, as well as two previous full 3D finite element models, one completed in Nodal from COWI and one in ANSYS from the University of Bristol. Based on all the available data and existing models, we are building two novel finite element models, one using Midas and one using OpenSys. Midas was selected as a first step, as a calibration model, if you like, against previous models and, more importantly, experimental data. However, it has limitations. It is highly idealized, and using a commercial software is not the way to go if you want to interact with the data. So there are no model updating options here. To do this, we need to take a step further, and based on the calibrated Midas model, build a more evolved model in OpenSys. This one will include more features. For example, we can incorporate saddle friction, and more importantly, has strong modeling capabilities, allowing for advanced analysis to be programmed and incorporated to the model using MATLAB or Python code. So here is an illustration of the geometry and key structural features embedded into the MIDAS model we developed together with Dr. Raffaele De Risi. And as already mentioned, it serves as a first step, the calibration step, before building the OpenSys one. It is a three-dimensional finite element model. The geometry and cross-sectional properties of the bridge are based on the COWI nodal model, and it has three main advancements with respect to previous models. It includes interactions of the suspension rods with the suspension chains. The boundary conditions modeling the tower saddles have been modified to better represent the actual behavior, and the deck constraints have been calibrated to better match the experimental mode shapes. All structural components have been included, excluding the towers, who have been considered rigid. The deck inclination was based on the levels, as you can see here, measured during the survey that was carried out in 2007 on the bridge. And the deck cross-sections are user-defined. They represent the geometrical properties of the wrought iron. We have modeled the three separate chains. And the deck and suspension chain cross-sections are modeled as beams. This was calibrated, so we checked this, and the experimental data, the experimental end deflections and frequencies were matched more accurately with the beam elements. The suspension rods are modeled as truss elements and are connected to the deck and chains using very stiff, weightless beam elements. The interlocking of the suspension rods with the chain links have been also considered, and the saddles are initially modeled through rigid elements on rollers, free to slide without friction. The OpenSys model will include a friction option that will be more realistic, and will be also calibrated based on the observations of the response of our saddles. Now, if we go to the next slide. Now, how do we know that our model is realistic? How do we know how close to the actual structure our model is? The answer is that if we don't have data to calibrate it, we don't know. But in our case, we did have data. And first of all, we have measurements of the dynamic response of the bridge. Detailed vibration measurements were taken by a colleague at the University of Bristol, Professor John MacDonald. 27 mode shapes with the natural frequencies below 3 Hz were identified. And here you can see a selection of these shapes and were used to calibrate the model. So if we go to the next slide, we can see the experimental data used to calibrate the numerical model. We used a model assurance criterion, the MAC, to compare experimental and numerical shapes, and we got a very good match. The mean MAC for all the vertical modes was 0.973. To give you an idea what this means, values larger than 0.9 indicate consistent correspondence between the shapes. A very important remark here is that it took us 50 iterations to get there. Without properly calibrating your model against actual data, the discrepancies between your model and the actual structure will be huge. Which features of the model needs to be calibrated? It is a long and painful process involving the boundary conditions, how you constrained the movements of the deck, for example, how you model the saddles, how do you model the chains, what type of elements do you choose for the suspension rods? And this is something engineers should always keep in mind, that no matter how advanced the software they use might be, or how detailed their model might be, if they want to be realistic, they need data. So the next figure shows the numerical mode shapes in the calibrated Midas model. I won't stay long here. And the next figure, yes, now you will be thinking, okay, that's all very nice. You have shown us your finite element model of the bridge. How do you go from the finite element model to the digital twin? And this is a very exciting part of this story that Sam will elaborate on in the next part of this presentation. Thanks for listening.
Cool. Thanks, Elia. I think I've remembered to unmute. Oh yeah, no, I can hear myself, so presumably everyone else can hear me as well. Right, so how do we get to from a model that Elia has described to something that's automatically updating and validating itself based on sensor data? Well, the first thing what we need is some sensor data to compare against our model. I'm going to discuss first of all an initial deployment that we did of a structural health monitoring system on the Clifton Suspension Bridge, and then move on to our plans, funded partially by or completely by UCRIC, I think, to turn the Clifton Suspension Bridge into a flexible monitoring testbed that's going to have a lot more capability and a lot more functionality, and deliver us the sensor data that we need to build our Clifton Suspension Bridge digital twin. But starting with what we've done in the past, so we, as Elia mentioned, we've been working with the Clifton Suspension Bridge and the management organisation, the Clifton Suspension Bridge Trust, for quite a number of years now. And the first time we deployed sensor technology onto the bridge was something we called the Clifton Suspension Bridge dashboard. This was back in 2017, and this is a high level, quite artistic, if I do say so myself, illustration of what sensors we deployed and where we deployed them. And you can see from the illustration here, we put accelerometers at the 1/3 point along the bridge, because that was a good spot for measuring mode shapes, and also we included more accelerometers and displacement transducers at the end of the bridge. And this was based on a wireless sensor technology. What you can see at this high level, there are sensor sensors out on the bridge, and then the wireless sensor gateway that was installed in one of the staff toilets. And if we go next slide, please, Maria. I feel like Chris Whitty. It's very exciting. So this is a few photographs to show that we did actually do it. So we've got the wireless sensor nodes that we developed. They're based on they were based on off-the-shelf wireless analog to digital converters, but they had a very good open interface library for the management of the data, the management of the sensor network, and we plumbed in a number of displacement transducers, which are in the farthest left picture, the barrel-shaped objects, the displacement transducers for measuring the actual amount in millimeters that the bridge deck goes up and down. And then we have accelerometers for measuring the vibration. And then these things were strapped underneath the bridge in a couple of places. And so you can see us there. There are a team of us working very closely with the Clifton Suspension Bridge Trust, making sure that we were complying with all the health and safety and doing our method statements and all that sort of stuff, making sure that we were sort of, showing that we were interested in working with them for the long time. The relationship management with them has always been very important. And then the laptop that you see there was the wireless sensor gateway, which was used for managing all the data. Managing the data at least on site on the local bridge, sort of close to the bridge. And data would be forwarded then onto servers at the university. That had to be. It was done on quite a tight budget. So it was all a little bit sort of, I wouldn't want to say Heath Robinson, but it was all done with a certain amount of ingenuity, and this was just a ruggedized laptop that we had to stash underneath the toilets in the staff toilets. So we made sure it was waterproof, but it seemed to survive the length of the deployment. And this was battery-powered technology, so it couldn't be used for long-term deployments. But because it was quite straightforward to deploy, a single person. Well, it took quite a lot longer the first time we were doing it because we were working out what we were doing. But after that, we deployed it a couple of times, and by the third time we deployed it, it could be deployed by a single individual in only a couple of hours. So it was quite useful for if we knew that there was going to be some sort of unique event that would be interesting to monitor, then we could roll this technology out quite quickly, and we monitored things like a sponsored walk that went over the bridge and that sort of stuff, and got some very interesting data. Next slide, please, Maria. There we are, thank you. So this shows a little bit of what's referred to as the data pipeline that collected the data. So you can see at the top, there are the sort of three components that were installed out on the bridge. You've got a wireless A to D, analog to digital converter, which converts the analog signals, the voltages that come out of the accelerometers and displacement transducers, into a digital value, which it then encapsulates and sends over a sort of, those who are into this sort of stuff, a sort of Zigbee-like wireless communication to our ruggedized laptop that was stashed up nearby. This was developed by Lord Microstrain, the A to D, so there was a lot of sophistication in the platform that we used there. It was able to do the synchronization that obviously you need if you're going to be using this for inquiring into structural health modes and structural modes and that sort of stuff. But the reason the Lord Microstrain equipment was very useful and worked very well for us is because it has a completely open Python API, which means that you can wrap your data collection into a much larger software environment, and that's very important, as we'll discuss briefly, in integrating into a digital twin. A digital twin is going to have to be able to read all this data and do something with it, and for the digital twin software to be able to do that, there need to be the application interfaces for receiving the data, and it needs to be comprehensible and understandable to the digital twin in a way that that allows the rest of the software environment to use the data. Also, importantly, is the ability for the system to sort of shift the data around and move it in a way that that different applications and different parts of the software package can use. So our data pipeline involves something called a message broker, particularly the Kafka message broker, which allows, which is what they call a publish subscribe model. So lots of different software instances can subscribe to the Kafka message broker, and they can all be posted the data as it's received. And we were working at, well, we had 6 sensors, each operating at 64 Hertz. So we're not talking big data, to coin a phrase, but we're certainly we're talking, reliable chunks of data, and this was nowhere near the maximum capacity that we could have coped with just a single server. If you wanted to scale something like this up, you might need a bit more computing hardware, but it would certainly be possible. And then Kafka pushed the data into something called InfluxDB, which is a time series database and works via tags, where essentially data is tagged to say what sort of sensor data it is, where it was, which rod location, all that sort of stuff. And so that's very useful because your digital twin will probably need to query large chunks of historic data. And so having interfaces that allow it to do that is very important. We used this data pipeline because it's all open source and it's therefore free. So that was probably our driving motive at the time, but it's also very effective for integrating into these larger software environments such as digital twins. The last sort of the data sync to some extent when it came to the Clifton Suspension Bridge dashboard was the visualization of the data, which we did through an interface called Grafana, a graphical user interface called Grafana. If I go to the next slide, please. Thank you. And this is a brief animated GIF of what the Clifton Suspension Bridge dashboard looked like when it was deployed the last time. We're currently between deployments, as I'll mention in a sec, but you can see the displacement at the top, so the amount the bridge deck is going up and down, and then, but as in millimeters, And then the two plots below are at the two different locations, the vibration information, and then the last plot is the information from the weigh and motion machine, or the WIM, as it's sometimes called, which measures all of the vehicles, the weight of all the vehicles as they enter the bridge. Actually, it's a bit more complicated because the weigh and motion machine is an operational sensor run by the Clifton Suspension Bridge Trust to make sure that vehicles, not vehicles that are overweight, are flagged and aren't allowed onto the bridge because they might do it damage. But we were able to negotiate the necessary contracts. Well, contracts is a bit strong. We were able to negotiate the necessary agreements with the supplier of that technology to get the data from that weigh and motion machine. And that gives us a bit more of the sort of system input, the loadings and things that were being applied to the bridge as we were monitoring it, and allows us to understand a lot better the structural dynamics. Sorry, well, okay, well, sorry, Maria, I'll move on then. So that was the previous deployment. Now we're looking at being able to do something much more sophisticated and much more flexible, and a lot of that is revolving around facilitating the rapid deployment of technology that can be left out for a longer period of time. So previously, the batteries were a limiting factor. They could only last a month or so, or a couple of months if you wound down the sample rate. But now we have a main ring installed out on the bridge. And this gives you a little bit of an illustration of where it is. We've got 12 points along the bridge that we can connect sensors into. We also have a Cat6 Ethernet ring that's out there. It's not all, we haven't quite worked out the route back. Well, we've worked it out, but it hasn't quite, the cables haven't been pulled back to where the server is going to be, but we're now going to have a dedicated server installed, not in the toilet, which will make a big difference. And so we'll be able to very quickly deploy sensors. So the illustration there in the bottom left-hand corner is called a field DAC, a field data acquisition unit. That particular one's from National Instruments, and we'll be able to plug in whatever accelerometers, displacement transducers, or whatever sensing we need underneath the bridge deck, and it'll be powered by the mains power, and then we'll have a very robust Ethernet connection back to the monitoring server that we'll have. Next slide, please, Maria. And this is an illustration of some of the sensing technology that we're going to, hopefully, this is a bit of a wish list, this one, but you can see it's got a lot of detail on there, but there's a few things that we'd really like to know more about the vibration of the bridge deck in lots of locations. Anything below the bridge deck, because of the supporting infrastructure, the power and the comms that we've already had deployed, will be quite straightforward. There's some stuff that we still have to work out exactly how we're going to do, and the little thermometer symbols along the chain illustrate chain temperature, which is something that's very important for understanding the lateral forces that the bridge applies to the rock abutment that Elia was mentioning earlier. And so understanding that is very important, but we haven't entirely worked out all of the complexities yet of monitoring temperature out in those locations, because it's very difficult to get to the chains without all sorts of, well, harnesses and that sort of thing. And then how do you do the battery swapping and all sorts of things? So there's technical challenges to overcome, but certainly when it comes to the vibrations, displacements, and anything below the bridge deck, our flexible test bed enabled by the power and comms will make the deployment of technology a lot easier. We're also hoping to integrate more of the operational sensors that the Clifton Suspension Bridge use, such as CCTV cameras using computer vision for monitoring vehicle locations, as well as the weigh and motion machine and the toll barriers, which we already have visibility of. So that's the plan when it comes to what we'll put out on the bridge. Also, next slide, please, Maria. We have a range of sensors that we've bought through UCRIC that we're, well, not just sensors, but also a lot of the supporting technology that you need to enable these sensors. So sensing technology, what's referred to as data acquisition, so to sort of convert the raw sensor values into something that's more easily transported and managed in a database, the networking, and then compute power, processing resource. So we've got quite a lot of different capabilities that have been bought under UCRIC, and including all sorts of very exciting, like computer vision based strain gauges and that sort of thing. So part of the flexible test bed will or the idea behind the flexible test bed will be understanding how we can combine all of these different sensor technologies to inform the digital twin, Going forward, next slide, please, Maria. So when it comes to the data, well, collecting data is only part of the challenge. A big challenge when it comes to understanding how we're going to develop a digital twin is the complexity around doing automatic model validation. As Elia mentioned, the sophistication of the finite element models, there might be tens of thousands, hundreds of thousands of different parameters within a finite element model. Many, possibly all of which could be updated, or need to be updated for the finite element model to better match the real world structure. And using engineering judgment is the way that that currently the model is updated. But if you're going to do that automatically, then programming that into a computer is very complicated, and there are obviously uncertainties associated with it. So there's a real challenge there. Further challenges are surrounding data. There's a lot of different, data is obviously a huge part of any digital twin, and there are complexities not only around the security of the data, as we saw when working with the Clifton Suspension Bridge before. They weren't keen on the data being made public because of the insight it might give to someone. But there's also data structuring through, as we'll see, I think not in the next bullet point, but the one after. The idea is that these digital twins feed into a hierarchical chain of digital twins to some extent. So you have your city level, you have your infrastructure, so your bridge level digital twin, and then that will inform maybe a city level digital twin. And then the idea is eventually there'll be a digital twin for the entire country, or whichever country, maybe the entire world someday, who knows. And the idea is that feeding the data up to inform the digital twins above, as you might visualize it, will require an awful lot of sort of data management, combination of data, separation of data, and how you do that in an intelligent and scalable way is very complicated. And then obviously one of the big challenges with digital twins is convincing the industry that they do present value. And so one of our key challenges has always been, when working with the Clifton Suspension Bridge Trust, to make sure that we're including them and we're trying to address the problems that they perceive when it comes to the operation of their structure. That's one of our key targets. And I think I pass back to Maria at this point.
Yeah, we are quite tight on time. So just to say that we are submitting a paper about this, and we have to output in international conferences that has been postponed. So I think you know that the dissemination of papers at the moment is quite tricky for conferences. Nothing. I would like to thank you all, and also our partners, COWI, the Clifton Suspension Trust, AMP, and you again for the attention today. Thank you. Vale, I pass the word to you.
Thank you very much. Very interesting presentation. Let's wait for questions, if anything. But I have a question to Sam and to Elia. At which stage, basically, the work that Sam did helped refining the model that Elia developed? And which parameters did you find you needed to further adjust or change or improve?
Well, if I take the first part, so the sensor data allows you to understand empirically the mode shapes that Elia was talking about. So when she had the diagram demonstrating the different mode shapes of the bridge, that sensor data allows you to generate those mode shapes from the structure itself. So a lot of the past work that she was mentioning is deploying sensors out along the bridge, seeing how the bridge vibrates in different locations, and from that you can see what the actual physical mode shapes of the structure are. And so she can then, when it comes to building the model and outputting the mode shapes from her model, she can see how accurate they are, and that allows for validation. I'll let Maria answer. I'll let Elia answer the second part of the question because I don't know.
Exactly. Sam said it perfectly. He explained it perfectly. There are so many parameters that need to be adjusted. In terms of the mode shapes, more importantly, the boundary conditions. They were a big headache. We had to do 50 iterations to match them, to be able to match the mode shapes. So the constraints of the deck are a big issue. The saddles, the way they move, the inclination of the saddles, if you have friction or not included in your model. So there are so many things that need to be improved and checked. So
it was a back and forth check between your model and Sam's analysis, basically.
And the data, yes, and the data.
Nice. There is a question on the chat, which I'm going to read. How is the bridge more flexible than contemporary bridges?
The bridge is more flexible because it is very light. It is the deck is constrained in only in the two ends in a very simple way. The cables are also really light if you see the construction. So the bridges today are much more robust. They are not allowed to move as much, especially after the Tacoma Narrows bridge collapse. They are trying to be very careful about the hydrodynamic fluttering and all these aerodynamic effects. So they build more robust structures nowadays.
Yeah, a modern bridge would be large slabs of concrete, which don't bend very much at all, whereas the bridge deck of the Clifton Suspension Bridge is made out of these iron lattice girders with a wooden and bitumen layer on top, so it's significantly more flexible than the concrete slabs that a modern bridge would be made out of.
So how this approach to monitoring the structure differ from other similar bridges? Would a similar approach be applicable to longer bridges or different construction?
Yeah, it certainly would be. It depends. So you could certainly do something similar. The reason that the wireless technology was appropriate for the Clifton Suspension Bridge to some extent is the scale of the bridge, the size. Not actually that long compared to many sort of the larger pieces of infrastructure. And so if you were going to deploy wireless sensors, you probably need to have multiple nodes, and then you have data synchronization complexities and that sort of stuff. The reason we use that wireless sensing technology, as I said the first time, is because it's quite cheap and easy to deploy. So what you'd like, networking and power are always the biggest challenges when getting sensors. Well, networking, power, and access. Three of the biggest challenges when it comes to all these things, and so overcoming those hurdles will answer a lot of the sort of technical challenges you need when it comes to like instrumenting up any sort of bridge. But the principle certainly would be the same. I mean, all these environments are quite harsh to radio waves, to the RF that you need. Obviously, it's made out of iron, and iron doesn't propagate RF very well at all. So you have quite a lot of challenges to overcome, but certainly the principles would be the same. And when it comes to the data pipeline back end, you could use that for almost anything. Wouldn't have to be monitoring a bridge. It could be monitoring. We've used that same data pipeline for monitoring all sorts of things now, pollution sensors and electric bikes and yada yada. So yeah, it would be certainly appropriate. It'd be a sensible place to start if you were doing something similar.
The next question is related to what I've asked somehow. So Chris is asking, what techniques do you use to determine the mod shapes from the measured data?
That's probably more, well, that's either me or Elia. We both sort of work with it. Although a lot of the mode shapes were known from previous papers, the way that you have to do it, my understanding, and this is a little bit outside my comfort zone, so I may completely mess this up. But the way you do it is by moving, like looking at the amplitude of different frequencies along the bridge in each different location. You have to have what's referred to as a cross section of the bridge in each location, so you can see not just the vertical modes and the lateral modes, but you also have torsional modes, and each of those modes are superpositioned on top of each other. And so trying to pick out all of the separate frequencies at each different location along the bridge then can tell you what the different mode shapes are. If you see, it's a bit like if you imagine you've got your piece, if you're looking at the resonance of a piece of string, that will have a particular frequency at which it oscillates at, or a number of different modes that it oscillates at if you vibrate it. And the bridges as a three-dimensional structure has lots of these different types of modes, lateral, vertical, and torsional. And because you pick out all the different vibrations at different locations, you can see what the mode shapes are, because there'll be comparative amplitudes at each location. Is that close enough?
We have two more questions, which I'm not sure you want to, you still have the time to answer to them. Is that okay?
Yeah, that's cool. Yeah.
Okay. So is the collected data currently post-processed and used for maintenance? Who should be owing using it in the future?
Yeah, very good question. Very good question. So at the moment, the data we've collected so far doesn't actually serve too much by way of operational value, I wouldn't say. Like it's interesting to see, but it's quite like obscure to some extent, specific mode shapes. And that's why the model is so very important, because it allows you to tie variations in mode frequency to changes in the structure. Like if all you know is that the bridge has changed frequency ever so slightly, that's not all that helpful. But if you've got a model and you see that by running your model and changing maybe, I don't know, whatever, the Young's modulus on one of the rods or something, that's the sort of thing that I guess might change, and your model tells you that that would present the change in frequency that you've witnessed, then that allows you to do much more with it. It might mean that that rod needs examining or something like that. So the data we collect at the moment doesn't really help that much, but the idea is using a digital twin, you would be able to derive much more value from those from this sort of quite complicated data that you're collecting. In the future, I would expect all the data to belong to the infrastructure managers themselves to some extent, but I think generally where you find these things is that there'll be contracts within contracts within contracts. I mean, the idea is you're going forward, presumably, that a service like this would be operated by, I think we mentioned COE a few times, the principal contractor for the bridge. And the idea is that probably, although the data would belong to the Clifton Suspension Bridge, the systems would be operated by these sort of principal contractors, but it would depend on the contract arrangements between the infrastructure managers and the contractors and all that sort of stuff. But definitely, it wouldn't belong to academia, I don't think. But hopefully that answers the question.
Is the ultimate aim to have real-time correlation between the digital model and site measurements so that discrepancies draw attention to the need to invoke maintenance? If so, how long do you expect it to be before that intent can be realized?
That's also a very pertinent question. Does anyone else want to jump in? Yeah, I feel like I'm hogging. No, I'll carry on going then. So the idea, so to some extent, as Maria highlighted, you probably could do this sort of thing in absolute real time, but you'd sort of have to wonder why you were bothering if the data was only going to be useful at sort of like some regular periodic interval. So the way that operational processes often exist in structures at the moment is you might have a periodic review of a particular situation or a particular piece of the infrastructure. So the saddles, for example, you're only going up there once a month to have a look at them at the moment, and because of the rate of change of that component is slow enough that you don't have to look at it any faster than that, there wouldn't be any point in updating and validating or sort of twinning your digital twin any faster than that process review cycle, if you see what I mean. It might be that you look for a near real time. There are challenges with that though, because what you're having to do each time you validate is that your digital twin software is having to change lots of different parameters in the model in lots of different ways, and then comparing the mode shapes that are generated by the model, if we're using mode shapes as our example for how we validate. If you'll compare your mode shapes that you generate from your model with your mode shapes that you generate from your monitoring for each of those different model configurations. So you might have to run the model depending on depending on the number of parameters you have to update, which may be many tens of thousands, you might have to run that model many, many, many times. And so doing a real-time update is obviously computationally potentially impossible, and not necessarily beneficial. So I think you have to be, personally, I feel you have to be a little bit realistic with these sort of things and say that probably absolute real time may not be possible, but something that was usefully real time, which is probably better because you're wasting this compute resource, may be possible, I would hope.
Yeah, and just to add a brief comment, I think it's very important to understand the difference between real time and right time. So the scope and the motivation behind your digital twin should really inform the twinning rate, so the frequency of the updating of the link between the real and the virtual object. Again, because the higher frequency, of course, means higher cost. So you want really to know which is the appropriate frequency of updating that you need and the reason behind it. So if you don't need the real time or the near real time updating, then yeah, there is no reason why you should build the capacity to reach it.
Yeah.
You're mute, Vale.
Who are actually managing the infrastructure is very important, and understanding what they're processing.
Yes, I totally agree with what Maria and Sam said. This is exactly right. It's a decision that, you know, there are many parameters that affect it. So
I think with that we ended the Q&A session. But before concluding, I would really like to thank you guys because it was a very, very interesting seminar. Thanks for giving us those insights, and we look forward to any update on the project. Thank you all for joining, and stay tuned. The next lunchtime seminars organized by the Young Second Group. Thanks a lot.
Thank you very much for inviting us.
Thank you very much.
thank you.
Good afternoon. Bye.
Bye.
Bye.